Welcome. AP Physics 1, Working Energy 2, that multiple choice set. We're going to cut that one in half. It's 24 questions. We're doing 1 to 12. This is the first time you've seen one of these. I put the index cards in there so that when people are scrolling through the video on YouTube or whatever, that they can see which, because they're probably not going to watch the whole thing straight through. They're going to go to the problems they need help with. So this is number 1. An object is moving in the positive x direction while a net force directed along the x-axis is exerted on the object. Okay, so it is moving. The figure above shows that the force is a function of position. So earlier, in one of the earlier videos, if you haven't seen it, the concept here that you need to know is this: is in a force versus displacement or distance graph, the area under the curve is the work done. And in fact, if this is net force, it's the net work done. So, but we'll see. Shows the force is a function of, so I guess there's only one force, we'll call it the net force. What is the net work done on the object over the distance shown? So, the work done in this, for the first distance d, is going to be FO times d. Let's try it this way. There we go. The work done for this, and it would be positive, it's above there. So the work done here is going to be half of that, right? Because it's a triangle and it's the same base, same height. So it's going to be FO times D divided by 2. Here, that's going to be negative. Now I'm just going to make sure this is right. Let's make sure that makes a difference. So this is a force in the positive direction. The force goes down. Here the force is in the opposite direction. It's in the negative direction, but the displacement would still be in the positive. So this is negative work. I'm just verifying. So force is negative, but the displacement still left to right. That's positive. So this is negative F0D, F0D over 2. So this one and this one cancel each other out. So the force was going down, but it was still positive work, so it was still speeding the object up. But this then started slowing the object down. So these two cancel each other out. So it should just be this. I would go with that. Let me pause this recording and pull up the answers so that I can just double check to make sure I'm getting them right. Yes, I was right. Okay. So I have the answers in front of me, so if I do get them wrong now, I'll know. Moving on. Number 2. Number 2 says a block of mass 10 kilograms moves from position A to position B, shown in the figure above. The speed of the block is 10 meters per second here, and 4 meters per second at B. The work done by friction on the block as it moves from A to B is most nearly. Ooh, I like this question. I like this question. So what we know is, what we should know, is mechanical energy initial, if there is nothing like friction, what they call non-conservative forces, should be equal to the mechanical energy final. But in this case, this mechanical energy final should be less later, because friction can only remove energy. So there would be some work done by that non-conservative force of friction. This is what they want. So I need to figure out how much mechanical energy did it have at the beginning, how much does it have here, and whatever the difference is between them must be the work done. Make sense? If there was no friction, its kinetic and potential energies here should add up to be the same number as they did here. In this case, they're not going to. Let's find out. So your kinetic energy, your initial mechanical energy, is all in the form of the kinetic energy at A. There's no potential energy. We're just going to call this level here 0. So that's going to be 1/2 m, m's 10 kilograms, that's 1/2 10 is 5, times the velocity squared, so that's 500 joules. So once again, that is 1/2 10 kilograms times 10 meters per second squared. And that's how we got this original mechanical energy. All right, so what's the mechanical energy here? Well, at the end, up here at point B, it's got mechanical energy is actually in two forms. It has some kinetic energy still at B, and it also has a potential energy, gravitational potential energy at B. No spring energy, so we won't worry about that. So mechanical energy final is, well, let's see, 1/2 the mass, so that's 1/2 of 10, that's 5, times 4 squared, which is 16. So 5 times 16, just making sure I get that one right, is 80. So I got 80 joules of kinetic energy plus gravitational potential here. It rose up 2 meters. So it's mgh, so the mass is 10, g is 10, so that's 100, times 2 meters, that's 200. So its final mechanical energy is 280 joules. It started with 500. So it started with 500. It ended with 280. Well, that you can't just, it doesn't just disappear. It went into heat through friction. So whatever's left over must be the work done by friction. So if I subtract the 280 from both sides, the 500 minus 280 will give me the work done by that non-conservative force of friction. So that's going to be 220. All right, and yeah, it should be negative. All right, now that's a little strange here. Here it does not come out negative. Maybe I should rewrite this equation then. Yeah, you know what? Maybe this. There's nothing wrong with this, except if I do that, it does come out to be positive. So let's look at it this way. Maybe I should write it like this one. Mechanical energy original plus the work done by a non-conservative force would equal your mechanical energy final. If we had done it, if I had set it up this way, I think I'll be in better shape. Because here I would have had 500 plus the unknown work by friction equals 280. And then I would have subtracted 500 from both sides and got the work done by that non-conservative force is negative 220. So maybe we should, going on from here on out, I should write it like this. I will do that. And that way it's a better indication of whether the work done by the non-conservative force was positive or negative. Fair enough. That'll be a new adjustment on my part. That is correct. All right. Doing number 3. Pendulum shown in the figure above reaches a maximum height of h above the equilibrium spot. Assuming friction and air resistance are negligible, which of the following, so in this case that means mechanical energy initial should equal the mechanical energy final. The total energy of the Earth pendulum system as the pendulum oscillates. So I would take that it should always be the same. All right? Total energy, that would be the kinetic, and if they had said the total energy of just the pendulum and they didn't say this Earth pendulum, then technically you wouldn't count gravitational potential. That's why they have to say that. In this case, this includes gravitational potential and, of course, kinetic. So I would say the total energy is the same throughout. Now, notice that it's all in the form of potential here, and it's all in the form of kinetic here. But but at this point here, for example, it's a little bit of both. It's lower, so it has less potential, and it is moving, so it has some kinetic, has a little bit of both. But the total is always the same. So if it had 100 joules here, and this has to be 100 joules. And at this point, maybe it's, well, right halfway would be 50 joules of each. But still a total of 100. So you have to be careful about when they say that the total energy, in that case, they mean mechanical energy. So it's going to be constant throughout. All right. Number 4. My apologies for the ugly lines of the copy here. Planet is in an elliptical orbit. So there's some things we should probably know about elliptical orbits. We'll look at it in a second. Which of the following best represents the mechanical energy, careful, of the planet and the mechanical energy of the star-planet system as functions of time for one complete orbit? Okay. So when they just describe the planet, not the star-planet system, this means we don't count gravitational potential energy. We just look at kinetic energy. So from this perspective, we're just looking at what's the planet's kinetic energy as it goes around. And we'll talk about that in a second. This represents the mechanical energy. When they say the star-planet system, that's the kinetic energy of the planet plus the potential energy that it has. Okay. So let's take a look at what's going on here. What we want to know about this situation is this, is that as this thing goes around, it's an elliptical orbit, so it's not always the same distance. And by the way, they're not this elliptical, but this is just for an exaggeration, so you make sure you see it. Notice this distance and this distance are not the same. This is farther, so it would have more potential energy here, less potential energy here. But the total energy has to stay the same for the star-planet system. So really, we've already given away the answer to this one. This should be a constant. Because as it gets closer to the star, it should speed up. So in elliptical orbits, what you would want to know in this world is this. The velocity of the planet here, when it's closest, is larger than the velocity here when it's farther away. So it speeds up when it's close and then slows down out here and speeds up. Now, it's not as exaggerated as this in the real world. You would probably, if you were far enough above the orbit of the Earth, you would not even notice that it was an ellipse. But it is, and so because if it was this drastic, we actually would get. We don't have summer because we're closer to the sun. If we were this much closer, maybe, but that's not what happens. It's because of the tilt of the Earth. But we don't have time for that right now. So I'm looking at the total energy of mechanical energy of the system to remain constant. But I'm looking at the mechanical energy of the planet to have a high point and a low point. So let's take a look and see what we got. So for the star-planet system, that's this graph, I would expect a straight line. So this is my axis. So I would expect either that, no, or this, but not that. So I would expect a straight line. The negative part is because the way we look at gravitational potential energy when we're talking about really big distances. We say that zero is infinitely far away, and as you get closer, you get more and more negative in your potential energy. It's like falling into a really big hole. Zero is the ground. Well, then you can fall really far into the negatives, and you'll still hurt yourself. So it's the change in energy that gets you. So that's why it's negative. But really, straight line is the important thing there. Here, if you're just considering the planet, remember, we're just looking basically at the KE of the planet. This planet, based on what I've described to you about elliptical orbits, does not have the same kinetic energy. It's at a low point, then it gets high, then it gets low, and so forth. So, one of these two, but this one we already ruled out, gotta be that. And I'm right, as usual. Let's get used to that, shall we? Just kidding. All right. Numero 5. Constant force of 900 Newtonians. That's not really a thing. Newtons, sorry. Pushes a 100 kilogram mass up the inclined plane shown above at a uniform speed of 4 meters per second. Constant speed, okay. Okay. Power developed by the 900 Newton force. Okay, so power is work done divided by time, change in time, or sometimes change in energy divided by change in time, but either one will work. In this case, I think we'll go with work done. So work is force times distance, correct? So really, power is force times distance divided by time. And then we're going to get a little creative. We're going to say, well, wait a second, what's distance divided by time? That would be velocity, wouldn't it? See, so power is also yet another way of looking at power. Force times velocity. So I got 900 newtons worth of force, pushing something at a constant velocity of 4 meters per second. I'm going 3,600 watts. Power is in the unit, so a joule per second would be the unit. Right? Work is in joules, or energy is in joules. Seconds. Joule per second is called a watt. So a 60 watt light bulb uses 60 joules of energy every second. But they don't really exist anymore because we all use LEDs. Number 6. Ooh. Right. This one might be difficult to do because we haven't done rotation yet. So this might be one of those little bit of an unfair questions. Two objects are released from rest on the top of ramps with the same dimensions. So the ramps are the same dimensions as shown in the figure above. The sphere rolls down one ramp without slipping. Rolls. We haven't really looked at rotation yet. The small block slides down the other ramp without friction. Which object reaches the bottom of the ramp first and why? Right, okay, so you can't really answer this question. So if this is a question that you were like, I don't understand why, there's a reason, because we haven't done rotation yet. If I don't get anybody asking me about this, now granted you guys will be watching the video, this is the sort of thing when I don't get anybody asking me, I'm like, I know nobody's doing their homework because there's no way they could do this. But, what the heck, let's talk rotation. So here's the thing. The quickest way to look at this is this. Is an object that's spinning, so forget rolling for a second, but any object that's spinning, that's turning, has kinetic energy. It's called rotational kinetic energy. This makes sense. Recently I watched Thor Ragnarok, which is a, if this is something that is being watched by somebody to learn physics 20 years from now, it was a movie. Look it up. But anyway, and Thor would spin his hammer before, that lady, the mean lady, broke it. But he would spin it. And I don't know about you, but I ain't getting in front of that. Heck, if anybody's spinning a regular hammer on a string, I ain't getting near that. So, let alone Thor's hammer. So, point being is it wasn't moving around the room. It wasn't like he threw it. See, there would have what we call translational kinetic energy. If he's spinning it, it has rotational kinetic energy. So any object that is rotating has this thing called rotational kinetic energy. Right. So, does the block spin? Well, the answer is no. All of its potential energy here is turned into translational linear kinetic energy down here. It doesn't have to give up any energy to rotation. But our sphere friend here, when he gets to the bottom, some of this potential energy is in the form of rotational kinetic energy, because he's rolling. I don't know if he's rolling that way. I guess he's rolling this way. But because he's spinning, that's part of rolling, some of his energy is in rotation, and the rest of it is in translational kinetic energy, which means he's not moving as fast. So he would not. If you drop these two, he's gonna take him a while to get going, because some of that potential energy has to get him spinning and moving. So this should reach the bottom of the ramp first and be going faster translationally, linearly. No. The block, because it does not lose mechanical energy due to friction. What? The block, because it does not gain rotational kinetic energy, but the sphere does. D. Yeah, that's a rotation question stuck in here, but I did not anticipate, because rotation's supposed to be... Well, anyway, we're just going to move on. Doesn't hurt to preview things, actually. 7.